Ways to charge objects. There's three main ways that we're going to talk about charging objects in my physics class. The first one is the idea of charging by friction. Now, in our SMORG, one very common way of charging an object is to physically rub a balloon against your shirt, for example. When you're doing this, basically electrons are being transferred from my shirt to the balloon. Now, since the balloon is an insulator, the electrical charge has to kind of stay right around here. It cannot flow around the balloon because insulators don't allow electrons to flow around too much. So electrons are transferred by rubbing one object against another. So originally, right now, my shirt has about the same number of electrons as protons, and they're pretty evenly distributed. The balloon has protons and electrons by about the same number, and they're pretty evenly distributed. Both of them are neutral at the moment. But if I start rubbing the balloon against my shirt, in essence what I'm doing is I'm transferring electrons from my shirt to the balloon and creating an excess number of electrons on the balloon. My shirt, on the other hand, has a deficiency of electrons. Since my shirt has more positive charges than negative charges, we call it the shirt is positively charged. And the balloon is negatively charged. But let's take a look. Have we created electrons? Have we destroyed electrons? Hey, that's a law in our book. And if I look at the whole thing all together, what can I talk about? The law of conservation of charge means that my net charge is still equal to 0, even though I've transferred electrons from one place to the next. So as long as I look at both things all together, net charge is 0. But if I were to charge this balloon and then hand it to somebody else, then I would be removing the balloon away from my shirt, and I would have a positive charge over there and a negative charge over here. So that's the first way that we can charge objects. The second is called charging by contact. And there's this device that students love. It's called a Van de Graaff generator. And basically it's a large steel sphere set atop this column that inside has a piece of rubber that in essence rubs against a shirt over and over and over again and dumps all of those electrons into this big metal sphere. Now, it's not plugged in, so the number of protons is pretty equal to the number of electrons. And if I were to touch it, you know what? Nothing really exciting happens. Mr. Fay is here. He has protons and electrons are evenly distributed. But if I were to plug it in, suddenly I start pumping electrons into this giant metal sphere, and that becomes very highly charged. What happens when I, Mr. Fay, go and touch this metal sphere? Well, some of those electrons that are being pumped in the Van de Graaff generator, now remember, electrons are like charges. They want to be as far away from each other as possible. If I bring my finger in really, really close, those electrons sense that, hey, there's some place that I can be, that I'm farther away from electrons. And they physically jump from one place to the next. And in other words, transfer electrons into me. I commonly refer to that as a spark, or I get shocked and I jump a little bit. Now, if I were to put my hand on the Van de Graaff generator, now what can all of these electrons do? As opposed to being confined to the Van de Graaff generator, they can start traveling down my arm, and I become part of this globe of the Van de Graaff generator. And I start building up a charge as well. So when I stick my finger out and you touch my finger, electrons are drained from me into you, and you get shocked as well. And so if we link hands, suddenly we have two people being an extension of the Van de Graaff generator. Now, let's say that I have my hand on the Van de Graaff generator and I'm holding somebody else's hands, and we're all being charged together. If somebody brings an item that is a better conductor than me, the electrons can jump to that item and down to the ground in this case, and in essence travel away from me and the person. Anytime the electrons move quickly, we perceive it as a shock. And so if somebody were to discharge the Van de Graaff generator, everybody that's in the chain gets shocked at the same time. Once again, electrons jumping, that is called a spark. There's a natural phenomenon, it's lightning. We're talking about billions and billions of electrons jumping from one place, clouds, to another, the Earth. And it happens at the speed of light. It's very, very fast, and that's what thunder is. The third way that we can talk about charging is by induction. One classic example of charging by induction is this device called an electroscope. And inside there are these incredibly fine little pieces of metal that are conductors. And you have a way that electrons can travel inside this Erlenmeyer flask through this large metal disc necessarily. Now I've drawn it as a sphere, but there's many different styles. Now currently our electroscope is pretty neutral. The number of electrons to the number of protons is pretty much the same. They're pretty evenly distributed. And these little metal plates are not attracted to each other or repelled. But if I bring a charged object next to it, I do a process that we talked about before called polarization. And in essence, I can make those leaves fly away from each other because I have polarized the electroscope. In other words, I've brought a charged object, my balloon, very close to the top, and all the electrons race to be as close to the charged object as possible, but leaving those little leaves inside of the oscilloscope to be very positively charged, and so they repel each other a lot. And in this, that we call this case polarized. You know what? The whole thing has a net charge of 0, but there is a congregation of electrons on one place and a congregation of protons on the other. So we've polarized our electroscope. Now, if I were to remove all the electrons that just happen to be on the very tippy top of our electroscope by doing things like touching it, in essence, I'm draining off those electrons from just a particular region of the electroscope. I'm draining off the electrons that are all living right here for just a little bit. And as I remove my finger away, there are fewer electrons in the electroscope than there were when we started, and the electroscope is charged. And we call that process charged by induction. So there's 2 steps to charging by induction. First thing you need to do is you need to polarize the object, and then you need to remove the excess electrons. By the way, vocabulary word, removing excess electrons is another word for grounding. And usually grounding means we take electrons and we present a way to get to the ground. That's where the word comes from. And so we need to ground the object that is charged by induction, creating a charged object.